Welcome to Calculus. Today we will investigate evaluating definite integrals. We'll take a look at two examples. Our first example is the integration from -2 to 2 of the function 2x cubed minus 3x squared dx. So we want to evaluate this integral using formula and also properties that we've gathered in our investigation of definite integration. So what I would like to start by doing here is to change this from the limits of -2 to 2 separate intervals from -2 to 0 and then from 0 to 2. Since all of our formula for the parent function integrations are from 0 to b. So let's do that change first. So I want to start off, I'll have my first integration is going to be from -2 to 0 of the function 2x cubed minus 3x squared dx. And then I'm going to add to that the integration from 0 to 2 of the same function, 2x cubed minus 3x squared dx. Now I do want to have my lower limit of integration, if I'm using properties like this, be 0. So my next step is to switch these limits of the integration on the first integral so that -2 is the upper one, 0 is the lower one. And remember, when I do an exchange like that, really all it does is switch the sign. So this is going to become negative integral from 0 to -2 of 2x cubed minus 3x squared dx. And then I don't have to change this second integral because it is already set up as a lower limit of integration of 0. So the second integral is unchanged, 2x cubed minus 3x squared dx. So now I've got the correct lower extreme of integration is 0. And what I want to do now is I want to dismantle this function. So recall, I can, if I can have components of an original function are added or subtracted, I can treat each of the terms as a separate function. So my next step is going to be taking negative integration from 0 to -2 of that first term, 2x cubed dx. So this is going to be now minus, so it's still minus because I'm on this first integral from 0 to -2 of -3x squared dx. And then I'll do the same for the second integral. Notice this is plus integration from 0 to +2 of 2x cubed dx plus integration from 0 to 2 of -3x squared dx. My goal now is to isolate the parent functions x cubed and x squared. So that kind of bottom line is we're going to factor out and let these coefficients pass outside the integral. So I'll just highlight the pieces that are on the move. And I got to mind the sign. As they pass outside, they're going to multiply times whatever sign's already on the integral. So this first one's going to become -2 times the integration from 0 to -2 of x cubed dx. But my next integral was minus, but the coefficient -3 itself is minus. So this is going to become minus -3 or +3 times the integration from 0 to -2 of x squared dx. And then the same passing of the constant outside the integration for these next two terms. So 2 integration from 0 to 2 of x cubed dx. And then my last constant coefficient's negative. The outside sign's positive, so it's going to be -3 integration from 0 to 2 of x squared dx. Once we've got the, in a way, the function unfolded and kind of parceled out into its individual parts, well, what I need to just note is that I now have these parent functions isolated. So notice the integral, in fact, the integrand of each of these is just a parent function. I got x cubed, x squared, and the same for the second two, or the second group of two, x cubed, x squared. So once I reach that point, I'm ready to convert now to just numerical areas. So we need two anti-differentiation rules here. We have one of them already. If I have the integration from 0 to b of x squared dx, that's going to be equivalent to 1/3 b cubed. We also need another one. And really what I'm responding to are these four that have been highlighted in the green. Two of them we have covered with that integration of the quadratic parent, but we need to catch what's the integration of the cubic parent. It's pretty easy, from 0 to b of x cubed dx. And I say pretty easy, it's going to follow the same pattern for anti-differentiation of the quadratic. So if that was 1/3 b cubed, this is going to be a 1/4 b to the power of 4. So that'll help us finalize this integration. So I'm going to start here on the left. So I just write that coefficient -2. And then for the x cubed integration from 0 to -2 dx, all I got to take, because I have 0, notice we were real careful to set our lower limits of integration as 0 so that I could use these properties of how to integrate the parent functions. So once I have that in place, it's really just going to be a 1/4. Well, yeah, a 1/4, because this is the cubic parent, times b. So b is always my upper limit of integration, -2 to the power of 4. And we'll keep going. So now I got +3. Now I'm dealing with the quadratic parent as the integrand. So that's going to be, as an antiderivative, 1/3. Upper limit of integration, again, is -2. That's my b. And then according to my rule for integrating the quadratic parent, that's going to be to the power of 3. Now to our second two integrations. So now I have 2. That parent function is the cubic, so this is going to be times a 1/4. And notice these upper limits of integration are positive, so that's going to be 2 to the power of 4. And for my last integration, -3 or -3, that one's the quadratic parent, so I'm going to use the coefficient 1/3 times the upper limit of integration 2 cubed. Once I have that in constant form, it's just simplifying. So one thing I notice, this first term, if I just kind of investigate what is the value of a 1/4 times -2 to the 4th. Well, -2 to the 4th is going to be 16. Positive 16 divided by 4 is 4. Times -2 is going to be -8. Well, I have here a similar expression. Notice the only difference in that third product there is the 2 is positive, but it's taken care of by the even power of 4. So in the second group, 2 to the power of 4 is 16, divided by 4 is 4, times 2 is +8. These two guys are going to cancel. We can go ahead and write that they both have a value of 8, but the first one's negative, second one's positive. They're ultimately going to cancel each other. Let's investigate for this second set of integrals. So I got, really here I've got an odd power. So notice it's going to preserve the minus sign. So again, you kind of consider them in pairs. -2 cubed is -8, times 1/3 is -8 over 3, times 3 is -8. So the kind of the value of this whole first one is going to be -8. And then our last integration, if I investigate it, the 2 here is positive. So 2 cubes 8 times a third is 8/3. But then the sign on this one is -3. So -3 times positive 8/3 is again -8. So here with these ones that are highlighted in yellow, I don't see a cancellation because they have the same sign. And when I add them together, -8 plus 8, that's going to be -16 square units. So our first example there is integration of a cubic function. Let's take a look at our second example. So here we have a kind of a different setup. We're trying to calculate the integral from 2 to 4 of kind of the unnamed function f of x dx. Now the way our function is defined is according to the 3 integrals given here in the direction. So we want to calculate this integral from 2 to 4 if we know that the integral from 0 to 1 of f of x dx is 1, the integral from 0 to 2 of f of x dx is 4, and the integral of from 1 to 4 of f of x dx is 7. So here we won't be using function rules. We just have to kind of think according to our properties. Can I write my given integral from 2 to 4 in terms of combinations of these 3 that I know values for? So what I want to start with is just thinking, okay, the integral from 2 to 4 is really going to be equivalent to the integral values of these 3 combined. So I just got to think, how am I going to combine these 3 that I know values of to represent the one that I don't know? So I do see that I have information about the function from 1 to 4. In fact, I have information about the function from 0 to 1 and then 1 to 4. So the way I'm going to start rewriting this is just thinking about how I can kind of re-represent these intervals. So first thing that I'm going to do is I'm going to say that this is equivalent to the integration from 0 to 4 of f of x dx. So notice I've just considered, okay, let's take that down to 0, minus the integration from 0 to 2 of f of x dx. And essentially what I'm doing there is I'm just saying, okay, if I don't know from 2 to 4, well, I can take from 0 to 4, just subtract 0 to 2 from that, and that would be equivalent to the integral from 2 to 4. Now I see that I don't have the integral from 0 to 4, so again I need to rewrite 0 to 4 as a combination of the ones I have. So I do have from 0 to 1 and 1 to 4, so I'm going to rewrite this as the integral from 0 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. And that represents for us the integral from 0 to 4 minus the integral from 0 to 2 f of x dx. So at this point, I've rewritten the original integral from 2 to 4 in terms of the 3 that I do have. And all that I've got to do now is substitute in these values. So for my first integral here, I have this identity. The integral from 0 to 1 of f of x dx is 1. So I'm going to make a substitution there. That's 1. Plus the integral from 1 to 4 of f of x dx. Well, that's given as the number 7. So I'll fill in there. And then my last integral is from 0 to 2. So again, just investigating what we have here. I have integral from 0 to 2 of f of x dx is 4. And that's going to be minus 4. And we just need to calculate here. 1 plus 7 is 8, minus 4 is 4 square units. And again, that's just using, in this case, really a property for splitting up an integral into its various components. What we would call, that's the additivity for adjacent intervals. Our last example is really taking two integrals and expressing them as a single integral. So what number 14 says is the integral from 7 to 3 of f of x dx plus the integral from 3 to 9 of f of x dx. And what we want to do is we want to combine those two as a single integral. So the thing I noticed first about number 14 is that on my first integral, those limits of integration are in a way from a greater value to a lesser value. And so I really don't want that arrangement, especially when I consider that the upper limit of integration is the same as the lower limit of integration of the second one. So the first thing I want to do is I want to apply reversing limits of integration property just to convert this so that it's the integration not from 7 to 3, but from 3 to 7 of f of x dx. And the way that we make that shift is just by switching the sign. Once I do that, I want to just bring the second one as is, so the integration from 3 to 9 of f of x dx. And to help me kind of see this, I'm really now looking at the reverse order. So what will help me evaluate this is it's really the integration from 3 to 9 of f of x dx minus the integration from 3 to 7 of f of x dx. And essentially what we're doing is we're taking the first really from 3 to 7 and just subtracting it out of that 3 to 9. And really what that's going to leave us is the integration from 7 to 9 of f of x dx. So notice all that I've done is I've really said, okay, if I'm taking out, if I locate like 7 there, it's in between 3 and 9. If I'm taking out this full interval from 3 to 7, what's going to be left is from 7 to 9. That's what's left, and that's what I'm reporting in my single integral there. Well, thank you for joining for this investigation of evaluating integrals using the properties and the formulae. See you soon.